Okay, ladies and gentlemen, let's make a start then. So welcome to the P3 first part of the Triple Science Nodes with Revision Hangout. What I'm going to try and do for you is to go through a few different topic areas in the first half of physics, give you a few practice exam questions. Now, the good thing about these Hangouts is, of course, they're interactive, so feel free to tell me if I'm going too quickly, I'm not talking loudly enough, if my terrible handwriting is not showing up properly on the screen. Just drop me a message onto Frog on the post section on the Hangouts there, and just let me know, give me a bit of feedback as I go. Okay, so like I said, you're going to need paper, pen, and a scientific calculator. Make sure your volume's turned up on your PC for you to be able to hear me clearly. So let's just make sure that I can use these things right. So make sure you've got your paper, you've got your pen, and a scientific calculator. Okay, so the topics that we're going to try and cover today are these ones here. So we're going to try and cover X-rays. We're going to look a little bit at ultrasound. Then the bit that is quite often people's favourites, lenses, ray diagrams, and then we're going to look at how they're useful in describing the structure of the eye, and then finally a little bit on lasers and optics and using lenses to correct vision. Okay, so this is just really the first half of P3, the medical part of it. So let's get started then. So the first topic that we want to look at is X-rays, and we want to be looking at how we create X-ray pictures, what a CT scanner is, and looking at kind of other uses of X-rays and safety precautions as well. So feel free to take notes as I go through this. You'll find that the notes that I'm giving you relate directly to the exam questions that I put in. So if you're taking notes and you're writing down the most important bits of what I'm saying, that should mean that you'll be able to answer my practice questions as we go through. So the first thing is X-rays, of course, are EM waves. So they're electromagnetic waves. And I'm deliberately writing like a toddler just to make everyone feel comfortable. I wouldn't want me to be writing too neatly. So they are electromagnetic waves. They are a really high frequency. So they vibrate backwards and forwards really quickly. And they are also a really short wavelength. Okay, so the waves are very close together. And they are high energy. Okay, now because they are so high in energy, there are of course dangers associated with that. The biggest cause of the biggest danger associated with X-rays is of course that they will give you cancer if you have too many of them. So they will try and limit your dose of X-rays if possible. Now, when we look at creating an X-ray image, you'll notice that there are of course black parts on the image and white parts on the image. So the screen is photographic film there. So just the same as you might have in an old-fashioned camera, so photo film. And the photo film starts off as being white. Okay, it starts off white, and of course it turns black when X-rays are hitting it. So this gives us the idea that in these parts here where the bones are, that the bones are absorbing the X-rays. They're not letting the X-rays go through them, and so they are blocking the X-rays, and so the film stays white. Okay, where the X-ray, where the photo film has gone black here, that is the X-rays are passing through that. So we can say that the X-rays are absorbed by bone, and they are transmitted by flesh. So if you look at the edges of the hand here and here where the flesh is, you can see that there is that the X-rays have passed through that, and so it's just a slight grey instead of being black. Okay, so they are transmitted by flesh and absorbed by bone. They're two probably the most important bits there. Now, when we talk about the quality of these images, we're going to talk about how these X-rays are really give you clear images. You can see very precise definition on the bone structure there, so they give you nice clear images. And of course, exam questions love comparing two things. So later on, we're going to be comparing X-rays to ultrasound that we're going to look at in a moment. Okay, so a little bit of safety then to do with X-rays. Down here we've got our lovely model wearing a beautiful lead apron. So lead will block it, will block the X-rays and prevent too much of a radiation dose. Now, you might also see that if you've had an X-ray, the technician will stand behind a LED screen. Okay, other ways to prevent harm is to just simply reduce your exposure. So the less time you are there, the safer it is for you. Okay, so like I said, uses of X-rays also goes as far as treating cancer. Because X-rays will kill cells, we can treat cancer with X-rays, and X-rays are right next to gamma radiation in the electromagnetic spectrum, so they're quite similar to gamma rays in many regards. Okay, now CT scanners. We've got a CT scanner here, and also a CT scanner here. Now, what a CT scanner does is it will build up a 3D image of the body. Obviously, what we have over here is just a two-dimensional picture taken from one angle. Well, a CT scanner is going to be able to take a three-dimensional image. And how it does that is you can see that these emitters and detectors, so here we've maybe got the emitter, here we've got the detector, but what it'll do is it will rotate around the body. And by rotating around the body, it takes pictures every time it moves, and so it can build up a 3D computer image where you can look at individual slices through the body. Obviously, good things about that is really, really clear, high definition pictures. Bad things about it, obviously, you've got getting a huge dose of X-rays, so they don't want to give those to everyone. Okay, so that's the quick run through for X-rays then. Now, bear in mind that on the next slide, we're going to be looking at ultrasound and be thinking about how we can compare ultrasound to X-rays. So the first thing to start off with is what is an ultrasound? Well, an ultrasound is it's a sound, but it's at higher or a higher frequency than human hearing. So you do need to be able to say that it is a sound, and it is just vibrations of particles, but it is above human hearing. Okay, and you will get marks if you say that as describing it, and you will also get marks for knowing that it is above 20,000 hertz. Okay, so that's what ultrasound is. Now, how ultrasound works is quite often used for scanning images of unborn babies. So here we've got one here. Now what they do is they, if we look at this image over here, is it shows that the ultrasound is transmitted, is sent towards a boundary. So for instance, the boundaries could be the outside of the skull of the baby, the top of the belly. We could have maybe the wall of the uterus in here. They're all boundaries and interfaces between slightly different mediums. So so there will be, at each interface, there will be a partial reflection. So as the ray comes in, a little bit of it will bounce back, some of it will go through. And that will happen at each interface. So at the top of the uterus, inside of the uterus wall, top of the skull, inside of the skull. Okay, so that each boundary, you get a little bit of reflection. And the detector, just above the womb, on the outside of the mum's tummy, that will detect each of the reflections, building up a picture. And how it builds up the picture is by listening for the reflections. And so if we look at the quality of the images here compared to X-rays, we can say that they are fuzzy. But there must be a good reason why we use these instead of X-rays. Well, of course there is that there is no harm from ultrasound. So doesn't cause cancer, which is a pretty big deal, really, especially when you're looking at little baby unborn children. So fuzzy picture, but no harm, doesn't cause cancer. So that's a big selling point from it. So you can see what's going on inside the womb there. Okay, there are other uses. We're going to go and have a look at exactly how it builds up the picture in just a second. But other uses of ultrasound. Not only is it used for imaging unborn children, but also used for removing kidney stones. or we could say destroying kidney stones, what they will do, what an ultrasound will do, is they'll fire a ultrasound signal at the kidney stones, and they will literally shock the stones to pieces. It will shake them apart. Okay, and they'll be small enough then to pass out of the kidney into the urine. Another use could be watches. So some watches are worth, hundreds of thousands of pounds. It could be a delicate watch with very fine mechanisms. So if you wanted to clean it, or polishing up very delicate items, you could use it for that as well. Now, one of the main uses of ultrasound is, along with imaging fetuses, is to look at flaws in construction materials. So, for instance, steel girders or screws, which are used to hold together bridges. If you imagine looking at a screw side on, okay, here's the thread on the screw. If you imagine that there was a slight crack in that on the inside of it, you can imagine that if you're holding up a bridge, that small crack in there could later develop to, your structure could fall apart. So for each screw, each girder, they will use ultrasound imaging to test for flaws and cracks on the inside. Okay, so how they do that is, we're just going to look at this image for a second. How they do that is, if you imagine, let's go back to the example of babies again. So if we've got a emitter is here, and the emitter will be next to a detector. So they are kind of next to each other in one thing. Let me just make that a little bit bigger so it doesn't stick out. Okay, then we're going to have this emitter and detector is going to be placed up close to the skin. Now, if we take a real zoom in version, here is skin. Okay, and this could be our flesh, and this could be our bone. Let's just assume we're going through and looking into someone's arm. So you've got a layer of skin, layer of flesh, layer of bone. Okay, at each boundary, there'll be a small amount of reflection. So let's say we're just going to angle the beam slightly so we can see what happens here. The beam will pass all the way through all of the materials, but at each interface, there will be a small amount of reflection. So that will go back to the detector, and that will give us our first peak here. Okay, it will pass through into the flesh and will rebound up here. Excuse my bad drawing. So that'll be the reflection from the front of the bone, and then again back here there'll be some reflection that comes all the way back from this area. And you'll have to excuse my terrible drawing like a toddler with this pen. Okay, so that'll be reflection from the back of the bone. So at each interface is a reflection which will be picked up by the detector again. And on the detector screen, you will see that there is a peak from each reflection. So of course, the thing to consider is, when you're working out the depth of the flaw or the crack, is that these pulses here represent the time it's taken to go from the detector to the interface and back again. So that this time here is the time taken to go there and back again. So if you just want to know the time to go there, you've got to divide it by 2. So let's have a look at a couple of examples. The first example we're going to use is example questions. The first thing I want us to do is to have a look at this question here. So what I'm going to do is I'm going to read it through as if I'm showing you the answers. That's not what I want to do. Now I'm going to go and read through it as if I was going to be answering it like you. So grab my highlighter, which will be on the exam table. So ultrasound and X-rays are used in hospitals to create images of the inside of the human body. To produce images below, the waves must enter the human body. Okay, so we've got ultrasound scan and X-ray. Okay, then in this question, you'll be assessed on your good English, organising information clearly, using specialist terms where appropriate. So, command word, describe. That definitely needs a highlight. Describing the features of ultrasound and X-rays. That's the first part of the question. Then, and what happens to each type of wave after it has entered the body? So what happens to each type of wave after entering the body? Right, just take a few seconds, jot down any ideas you've got. This is a 6-mark question, but the good news is we're only after 4 scientific points. Okay, so just take a moment. And don't forget, you can pause this broadcast at any time. You can rewind it if you don't get long enough. Okay, so if we start to think about how we could order the answer, if I just clear everything off the screen, you're going to see that this question comes in two parts. The describe part of ultrasound and X-rays, and then what happens to them on the inside of the body. Now, these questions are really just asking for what is it that your teacher has told you. So if we look at describing the features of those two things, we're going to need to give the features of what is an ultrasound, what is an X-ray, and then on the inside of the body, what do these two things do on the inside of the body? So probably a good place to start us off is to just have a look at how would we structure this question. So we're going to want features of X-rays, so describing the features of ultrasound and X-rays. Features of ultrasound, then what do the X-rays do inside the body, and what does the ultrasound do inside the body? Okay, so features of X-rays is what can you tell me about X-rays? And features of ultrasound, what can you tell me about them? How does the X-ray work inside the body? You know, how does it produce the image? And ultrasound inside the body, how does that produce the image? So if we just have a look now at some of the answers. So features of X-rays, they are, any one of these will get you the mark. So they are an electromagnetic wave, very high frequency, very small wavelength, or very high energy. Features of ultrasound, they are frequencies above the human hearing, above 20,000 hertz, or they're a longitudinal wave. X-rays inside the body. So what happens to them after it's entered the body? Well, they are transmitted by flesh. So the X-ray passes through flesh, but they are absorbed by bone. And take care not to say that they're reflected by bone, because they really aren't. The bone does take the X-rays in and stops them passing through. And then finally, ultrasound inside the body. There is a partial reflection at each of the interfaces. Okay, so one more practice question, and this is to do with flaws inside the steel bolt. So I'll run through this question as if I were a pupil answering it. So the diagram shows a very high frequency sound. I know that's ultrasound. It can be used to check for internal cracks in a large steel bolt. The oscilloscope trace, that's this here from the oscilloscope trace shows that the bolt does have an internal crack. So we've got our transmitter and detector is right next to the end of the bolt. There's your steel bolt there. Okay, now on this screen here, we see that 1 centimeter represents a very small number of seconds. So that's each square there is worth that amount. Now, it says use the information in the diagram and the equation in the box to calculate the distance from the head of the bolt to the internal crack. Notice I'm highlighting command words in here. What is it actually asking me to work out? Well, it's just from the head of the bolt to the internal crack. Okay, so how are we going to work this out then? Well, the first thing we're going to need to do is to work out how long has it taken for the pulse to go from the end of the bolt to the crack and back again. Okay, because that's what this peak is here. So the time is going to be here. If we look along here, we've got, let me just clear all of this off the screen. So we've got 1, 2, 3, 4, 5 centimeters on there. So that's going to be that number times by 5 to tell me how long it's taken for it to go there and back again. Now on my calculator, that's going to be 4 zeros and 25 seconds. Okay, it's just that number times 5. Okay, but that's to go there and back again. Okay, so just remember that. Now the distance then, we're going to use this equation down here. So my distance is going to be my speed, which is 6,000, times by this answer up here. Okay, now that's going to give me an answer of the distance being 0.15 meters. But that's to get there, to go from the detector up to the crack and back again. So I need to divide that by 2 to find out just the distance to the crack. So the answer is going to be 0.05 0.75 meters. Okay, and that'll get you the 3 marks for that. So do remember, if you want to watch this back, you can pause at the start of these questions, you can have a go at them yourself and watch back through my workings again. This type of question comes up quite a lot, so really useful for you to have a good hang of it. Okay, next. Okay, now if we want to look at lenses, before we look at lenses, we need to look at, well, how do lenses work? Well, lenses work because they bend light. And refractive index is a measurement of how much a material bends light. Okay, we can see here is a example you'll all be familiar with. We've got our incident ray of light coming into the block. This glass block here is bending the light, as we would expect, and this is more dense and is coming out of air. So we can see that it's bending light towards the normal. And just to make sure that you all know, that there is the normal. Okay, so what can we say about refractive index then? Well, the ratio of the sine of that angle over the sine of that angle always gives you the same number for a type of material. Okay, so one type of material, be it glass or a particular brand of plastic, will always bend light by the same amount, by the same kind of ratio of sine I over sine R. And that is this equation over here. Okay, and this is where we need our scientific calculators for this bit. Now, this equation here only works for less dense to more dense. So this equation only works for this type of example. We've got it going from air into water or air into glass, from less dense to more dense. Okay, so be aware that that equation has to be flipped upside down to work for more dense to less dense. Or, Alex Forster helped me out with this one, gave me a good way of explaining this. We can think of this as sine of the bigger angle over sine of the small angle, if you can read my lovely handwriting there, is always equal to n, no matter whether it's going from more dense to less dense or less dense to more dense. Doesn't matter which way round, that equation will always work. But if you want to go the traditional way, this is the equation for less dense to more dense. Flip the sine I and the sine R for more dense to less dense. Okay, now just to help us out with a bit of rearranging here, they will quite often ask us to work out R, or they'll ask us to work out I. Now be prepared on having to rearrange the equation to get I on its own or to get R on its own. So let's just have a look at solving it to find I. So if I want to find I need to times both sides by sine of R. If I times both sides by sine of R, I've got sine of R over sine of R, they will cancel each other out, turn into 1, and the sine of R will disappear from that right hand side. So I can say that n times the sine of R equals the sine of I. Okay, so as long as I do the same thing to both sides, I'm going to times both sides by sine of R. That'll cancel out on that side and move it over to that side. So here's my kind of intermediate step, but I still want to get I on its own. So I'm going to go, I need to take the inverse sine of both sides. It's a bit like dividing by sine, but there's no such thing as really dividing something by sine, because sine isn't a number, it's a function. So we are going to take the inverse sine of both sides. So I equals, and I'm just flipping the equation round now, so I equals the inverse sine, so sine to the -1 of all of this. Now inverse sine is not a scary thing, it's just a button on your calculator. Okay, so sine inverse sine of n sine of r. Okay, and that's how to rearrange it for I. In the next question, we're going to rearrange it for r. But again, a similar thing, as long as you do the same thing to both sides, should be fairly straightforward. Okay, so if I get rid of this and we look at our next question. Here's a classic question. They're going to give you the, well, let's read it all the way through. So figure 2 shows what happens to a ray of light as it meets the boundary between air and water. Now the refractive index of the water is 1.3, so that's my n, and it wants me to find r. Now it tells me there the angle of incidence, I, so I can even put I there, and it wants me to find this angle here. Now my equation is just here, but I want to find R this time. Okay, so again, feel free to pause it at this point if you want to have a go at the question and come back to it and push play when you're ready for the answer. So if we look at rearranging this equation, then we need to put sine of r onto the left-hand side. So if I times both sides by sine of r, that will move it up there. So n equals sine I over sine of r, and then n times sine of r equals sine of I. Okay, an intermediate step. Now I want to get r on its own, so I've got to divide both sides by n. So sine of r equals sine of I over n. Okay, now I need to get rid of this sign, so I have to take the inverse sine of both sides. So it's going to be r equals inverse sine of sine of I over n. Okay, now that I've rearranged my equation, I can put in my substitutions. I always find that doing your rearranging before you put in the numbers is a really good bit of practice for you for A-level and for degree-level physics, because the equations are going to become so big and long and cumbersome, you don't want to have numbers in there. So that's the equation I need to do. So now I'm going to put in my numbers. So it's going to be sine to the -1 of sine of 35 over 1.3. And just in your calculator, do sine of 35 first, divide that answer by 1.3, then with that answer, take the inverse sine of that. Okay, and we should find that that gives us an answer of 26 degrees. And I've just rounded it off to a whole number because it gives us the other angle in a whole number as well. Okay, so you should find that that gives you an answer of 26. Okay, like I said, if afterwards you want to go back and you want to retry the questions, just pause it and go back to the start. Okay, lenses then. So now we're going to start to look at the two types of lenses and what can we, what kind of science can we put to these lenses? Well, lenses come in two types. So here we have a converging lens, as it says just up there. So converging, con means to come together in Latin. So con is bringing the rays together. And here we have a diverging lens, and di means to go apart, like a diverging river, so to move apart. So converging lenses bring the rays together, diverging lenses bring them apart. But they're not only known as converging and diverging, they're also known as concave and convex. Now, if you're being asked about concave and convex lenses, well, if we look at the concave lens has caves on either side of it. So that is our concave lens, and that is going to spread the rays apart, as we can see in our diagram up the top there. And we have convex lenses, which are going to bring the rays together. So we've got rays coming from the distance, you know, coming from the distance, which should be parallel to each other. Let's draw that one again. And this one here is going to bring the rays together. This one here, oh, silly me. That one is going to put the rays apart. Okay. Now, as long as you know that for the two different types of lenses, that's going to help you with your ray diagrams. This type of lens will spread the rays out. This type of lens will bring the rays together. Okay. Now, there are another couple of things that we can gain from these diagrams. We've got the focal point. So the focal point is where the rays cross. On this type of lens, it's where the rays appear to be coming from. So of course, we can't see the rays. The rays aren't really coming from this point, but it looks as if they are if you're on this side looking back. Okay, and the focal length is the length of the center of the lens to the focal point, from the focus to the center of the lens. Okay, now it makes sense that the shorter this distance here, the stronger the lens, because we're going to measure the strength of the lens by how much it bends light. So the more closer that these rays come towards the lens, the stronger, the more powerful the lens. So power is measured by 1 over the focal length. So this length here. So 1 divided by that length gives us the power. So the shorter the distance, the more powerful. Okay, or in other words, the more light is bent by a lens, the stronger it is, which makes sense. Okay, that looks like about it for that part of lenses. So now, this is where we get onto drawing ray diagrams. Something which at first sight could appear quite complicated, but thank God that there's some really straightforward rules for us to be able to apply to this. So the chances are that you're going to be asked to draw the image. Now, I just see a question there from Zoe. No, there's no unit for refractive index, so it's just a number. Okay, so if you're going to be asked to draw an image on these ray diagrams, well, we need to know some rules for it. So let's have a look at a couple of the rules. So if I want to know where's my image going to appear on this side, is it going to appear over here? Well, this is how to work it out. Okay, 3 golden rules of drawing ray diagrams. The first rule: draw a ray undeflected straight through the lens. Now, I don't have a ruler, so this is going to probably look a bit wonky, but roughly speaking, we draw a line straight through the lens, a straight line, not like that. Secondly, you're going to draw a ray parallel to the axis. So here's my axis, this black line through there, and then bend at the lens and go through the focus. So I'm going to go straight parallel to the axis, and then when in the center of the lens, I'm going to pass through the focus on that side. And if that's not enough for you to be able to work out where the image is, don't forget that the image is where the lines cross. If you wanted to, you could do a third line as well. So draw a ray through the focus on this side, and then bend at the lens parallel to the axis. So go through the focus on this side, hit the lens, and then go parallel. Now, just because I knew my drawing would not be up to much, we've got a replacement. So let's have a look at this one. So here we have our ray through the center of the lens, undeflected. Our second rule: draw a ray parallel to the axis, then through the focus, then on this side, through the focus on this side, then parallel. And the image appears where the rays cross. So of course they would carry on. Now, if I look at another couple of examples, we've got this picture here. So this will be where our object is outside the focal point, and this is a concave lens. So if you remember, on a concave lens, I said that the rays will split apart. Well, we can still apply these rules to a concave lens. We just have to be a little bit more creative with it. So the first rule still applies: draw a ray undeflected through the center of the lens. That's this ray here, straight through the middle of the lens, through the axis, through the center of the lens. Okay, secondly, draw a ray parallel to the axis, and then bend at the lens through the focus. Well, I'm going to draw that parallel to the axis, and you might think, oh, well, in the last diagram, I drew it along here. I drew through the focus here. But we know that this type of lens doesn't bring the rays together. We know this type of lens spreads them out. So if they're spreading out, it has to be coming off up here somewhere. So how do I know how to draw it up here? Well, what do? I have to draw a dotted line back through the focus on the left-hand side. Okay, and because I've drawn that line back, that's going to tell me where my image is, and the image is just going to appear where the rays cross. Okay, so the rules still apply, just have to be a little bit more creative with how we apply them. Okay, this lens, we've got our object inside the focal point, and again, if we were to just apply these rules, draw a ray undeflected through the center of the lens, that's this ray here. Draw a ray parallel to the axis, and then through the focal point on the far side. Okay, well, that's nice and straightforward. But I said that the image appears where the rays cross. Well, we could say that in this bit here, we don't have any rays crossing. So again, if the rays don't cross, just dot them backwards. Just keep going backwards, and you'll find that eventually they will cross. And where they cross is where we can draw the image. Okay. Now, there's a couple of bits of information we need with types of images. So if we've got our object is, let's say, this big, and there's my axis, there's my lens. Now we can say certain things about the image. So if the image is bigger, we will say it is magnified. Okay, if the image is smaller, we will say diminished. If the image is flipped, we will say inverted. And if the image is the right way round, we will say upright. Now, this one quite often gets people. So, is the image virtual or real? Okay, the easiest way to think about it is if the image appears on this side, it's real. If the image appears to be coming from somewhere over here, let's say here or here, then we will say that if the image appears on this side, we say virtual. Okay, another way of thinking about it is that real images can be projected on a screen, and virtual images can't. So a virtual image is something like a magnifying glass where the object, where the image appears to be maybe bigger than the object. We can't project a magnifying glass up onto a screen. Okay, so let's have a look at applying some of these rules then. So again, just hit the pause button if you want to stop at any point and have a go at the question before I go through it. So if we look at applying, on this question, we look at applying our 3 golden rules. So what are the 3 golden rules? Draw a ray undeflected straight through the lens, draw a ray parallel to the axis, and then bend at the lens through the focus, and then again draw a ray through the focus and then bend at the lens parallel to the axis. So, as it says up here, complete the ray diagram to show how the lens produces an image of the object. And the next question is going to be, give 2 words to describe the nature of the image. So only 2 words, and up here, just complete the ray diagram. If we look at completing the ray diagram, first one, draw a ray undeflected. Well, that is going to be the ray straight through the center of the lens. Okay, then draw a ray parallel to the axis until it hits the lens and then bend through the focus. So that's going to be like so. And then now, we're already pretty happy with where the image should be. The image should be over here, but let's just double check it by doing our 3rd rule, making sure, okay, if we go through the focus on this side, hit the lens and go parallel, so our image is going to appear here. So if we wanted to now describe this image, well, what can we say? Well, it is inverted, it's upside down. If we compare it to the original object, it is diminished. And it is a real image, okay, because it appears on the right-hand side and we could project it on a screen if we wanted to. So any 2 of those for your 2 marks there. Okay. So one more ray diagram question, just to make sure we're confident at it. So again, we're going to apply the 3 golden rules again. And the 3 golden rules are, first off, draw a ray from the top of the object straight through the lens. Now on this one, I'm just going to highlight in the question because of course I shouldn't jump into doing the question before I've read it properly. So it's a converging lens, so that means the rays should come together. Draw 2 rays from the top of the object. Now I'm going to start off by drawing 2 rays, but I'm also going to draw the 3rd ray as well, just to kind of show you how you would do it if you needed to in this type of question. So first rule, straight through the middle of the lens. Quite happy with that. Second rule, parallel to the axis and straight through the focal point on the other side. Now, the rays don't cross over here. So this is where I need to kind of be a bit more creative. If they don't cross over here, how can I make them cross over? Well, if I draw dotted lines backwards, we'll find they cross over here. Now what you'll notice is I've just put in some weird shape over here. Let's get rid of that for a second. If I draw the rays backwards, my image is going to appear over here. Now what I've decided to do is I've decided to put in the 3rd ray just to show you where it would go. So the 3rd rule is to draw a ray through the focus on the left-hand side to hit the lens and go parallel to the axis. Well, this is actually what I've done here. So here's the object, there's the top of the object, and I've drawn a ray from the top of the object through the focal point. But of course, it's bending, it's actually going away from the where I know the rays are going. So I continue it up until this line. This line represents wherever the lens is, and then again, my rule says that it has to go parallel to the axis. So there it is. So if I had to draw all 3, that would be what the 3rd one would look like. So we can see here that the rays are spreading out is exactly as we would expect. Okay, so if I look where the image is now, it's on the far. Oh, on the far left. And we could describe that image as well. We could say it's magnified, we could say it is virtual, and it is upright. Okay. If we now start to look at structures of the eye, they want you to understand the structure of the eye in regard to talking about focusing, and particularly how light enters the eye, controlling the amount of light that comes into the eye. So if we look at these, if we look at the cornea and the lens, these are the bits. The cornea is the layer over the top, and the lens there. The two of those are responsible for most of your focusing, well, all of your focusing. The cornea can't change shape though. So the cornea does lots of focusing, but the actual kind of fine tuning of it to get the image to project on the retina is going to be done by the lens. Now the lens itself can't change shape. It has to be changed shape by the ciliary muscles and the suspensory ligaments. Now, the ligaments are always holding the lens flat. So the ligaments, when they're taut, they're holding the lens flat. So if I want to make the lens go rounder, then so the lens is being held flat by the ligaments, and the ciliary muscles are going to have to contract. They work against the ciliary muscles work against the ligaments to make the lens rounder. So if I want to make my lens flat, I will relax my muscles. Now, this makes a bit more sense when we think about, when we look at things close up, we find that our eyes have to work harder to look at them. If you look at things in the distance, your eyes are relaxed, and that's because of the ciliary muscles. So the closer objects will require tense muscles to bend light more. So you'll need a rounder lens to bend light more. And when you're looking at far away objects, your ciliary muscles relax so that your lens is nice and flat. Okay, now if in the exam you've forgotten which way round it works, just look off into the horizon and relax. And then when you look down at your exam paper, you'll find that you tense up, and those are your muscles tensing up, looking at something closer to you. Okay, so that's how the ciliary muscles work and the ligaments. And then the last thing that you'll need to know about is the iris and the pupil. So the iris is the coloured part of the eye. So when we look into someone's lovely blue eyes or brown eyes, we're looking at the iris is the colour, and the pupil is the black hole. So the pupil, if you like, is just literally a hole at the front of the eye. That's what the light goes in through. But the iris changes shape. The iris will make the pupil smaller or larger. Now the iris makes the pupil smaller in bright light to prevent damage to the retina. So the retina is all the way around the back of the eye, and that is what has the photosensitive cells on it, your rods and cones. So there is your retina at the back there. Of course, there's your blind spot where the optic nerve is. Okay, so the iris prevents damage in bright light to the retina by closing the pupil to reduce the amount of light that comes in, and relaxes to open the pupil to let more light in dim light. Okay. Now, likely questions. So how does the structure serve a purpose? How do we focus? How do we alter the light coming in? Those will be the two things you get asked. How do we focus? How do we let the light, changing amounts of light come in? Now, you will also be asked to compare the eye to a camera. So when we look at comparing an eye to a camera, you need to compare how in the camera, the lens, which is here, the lens will move backwards and forwards. It will either move, and we need to describe it moving compared to the film at the back. So it'll either move towards the film, or it will move away from the film. And on the back of the camera, up here, we have photographic film. And you need to be able to name that. Or we can say for a newer camera that is electronic, we have a CCD, which is charged coupled device. And that's really, they're just photosensitive, tiny little collection of photosensitive cells that will send an electrical signal back to the computer inside the camera. So it's either photographic film or it's a CCD at the back of the camera compared to the retina at the back of the eye. So I said for focusing, all that can happen to focus is the lens can move either further away from the film or closer to the film. Well, in the eye, it's not like that. In the eye, the lens will change shape. The lens doesn't move backwards and forwards. The lens changes shape, and it will either get rounder to look at objects which are closer up, or it will get thinner to look at objects which are far away. Okay, now in the camera, if you zoom in to look at something close, the lens will move away from the film, and to zoom out to look at something far away, it will move closer to the film. Okay. So also comparing the iris and the pupil, they control the amount of light going into the eye. Well, you might also have an aperture or some sort of variable opening at the front of the camera that you can open and close to change the amount of light coming in. Okay, so if we now have a look at a typical question, this will be labeling the eye. So again, just pause it here if you want to have a go at labeling the eye. For those of you that are just doing it with me, here we have the retina, that's on the back of the eye. Here we have the ciliary muscle. Now I was wondering there, could that be the ligament? Well, thankfully the ligament doesn't appear down here, so that's got to be the ciliary muscle. I don't think my handwriting would get many marks in the exam. Ciliary muscle. And here we will have the iris. So the iris is just around the outside of this gap here, which is a pupil. And of course this funny shaped thing here is the lens. Okay, so next type of question, like I said, be prepared to have to comment on the functions of both of these. So describe the functions of the ciliary muscle and the iris. So of course, you know, when you come to a question like this, it's pretty much what has your teacher told you about these two things? So if we have a quick look at the answers, we need to be talking about how the ciliary muscles change the shape of the lens to look at objects far away or close up. Are the ciliary muscles going to tense up? Are they going to relax? What effect will that have on the shape of the lens? Will it make the lens go rounder or make the lens flatter? And similarly with the iris, is the iris going to be making the pupil smaller in bright light or making the pupil larger in dim light? So if we just have this is a 6-mark question, so if we just have a quick look at the answers up here, again, please pause it if you wanted to have a go at this on your own. So we can see that the ciliary muscle, well, its job is to change the shape of the lens. So it relaxes to flatten the lens for objects which are far away from a distance. It contracts to a round shape to focus in on close-up objects. Okay, so we definitely want to say that that's what the job of the ciliary muscle is. We'll say it flattens when you're looking at things far away, and it makes a round lens for close-up objects, saying it relaxes and contracts to do those two things. So you might think that it's kind of counterintuitive. You might think that it's quite odd that it contracts to create a round lens when the round lens is shorter than the long lens, than the flat lens. So, but it's because the lens is always being pulled apart by the ligaments, and the muscles actually have to work against the ligaments, if you like. Okay, and then the iris, it controls the amount of light entering the eye, expands or relaxes, making the pupil smaller in bright light, contracts, making the pupil larger in low light to protect the retina. Okay, so last 10 minutes or so of this Hangout session. Don't forget you can rewind, watch these again on the archive facility, and that could be quite a good thing for you to watch these a couple of times, have a go at the questions, maybe second time round. So comparing camera to the eye, you'll more than likely be asked about comparing the functions of the two things. So where are the images focused? If we look at the missing parts here, images are focused, well, in a camera, it's going to be either a camera film, photographic film, or the CCD. I would imagine you'd only need to write one of those in to get them up. Okay, and the variable opening where light enters. Well, I mean, the variable opening is controlled by the iris, but where the light actually enters, is the pupil. And it does say the mark scheme would not allow iris for that, so that's going to be pupil there. Okay, good. Now, if we want to correct vision, if we want to fix people's short-sighted or long-sightedness, and I'm particularly short-sighted, so I suffer from this, we need to put lenses in front of the eye. Now, the whole purpose of the eye is to be able to create a sharp image on the back of the eye, on the retina. So if we look at this normal, inverted commas, normal eye, the rays from a distant object are focused perfectly by the lens. They're focused straight onto the back of the retina. But if we look at someone who is nearsighted, so short-sighted, like myself, I can't see things which are far away, the images are being focused inside the eye. So it's producing a fuzzy or blurred image on the back. So I can't see things that far away. Now, if you're far-sighted, so you're long-sighted, you have trouble reading, your images are being focused behind the eye. Okay, now if we want to correct these two different types of visual impairments, then we need to place lenses in front of them. Now, you can work out in the exam which lens it is, because there are two types of lens. The ones which spread rays out, and the ones which bring rays together. Okay, so we need to be thinking about what is it I'm going to need on this type of eye, and what is it I'm going to need on this type of eye to make it now focus straight on the back of the eye there. Well, if the rays are falling short, I'm going to need to spread the rays out a little bit. By them being spread out a little bit more, they will now appear on the back of the eye. And again, for this far-sighted one, I want the rays to be bent slightly more, so I just need to pop a different type of lens in front. Now, just to prove that, okay, here we've got our corrections. You see that this type of lens has spread the rays out a little bit before they enter, so that they can focus perfectly on the back of the eye. Again, with these ones, these will bring them together so that they can focus, again, perfectly on the back of the eye. So now these types of, these problems here with the focusing not working properly, we can say that this is for two possible reasons. I mean, you're short-sighted here. You're short-sighted here because either your eye is too big, which sounds pretty insulting, to have a big eye too big, or lens is too powerful, which sounds a bit better. So I'm going to say I've got that. So I've got a super powerful lens. If you are long-sighted, your eye is too small. Which again sounds pretty insulting, or your lens is too weak. Okay, so that's how we could describe what causes those conditions. Okay, so now if we look at this practice exam question, well, we can see here that the rays are being focused inside the eye. They should be crossing over at the end. So we could say that maybe the lens is too strong there. So if the lens is too strong, that must mean that this is short-sighted. And over here, so to be able to correct this type of lens, we're going to need a lens which spreads the rays out just before they enter. So if that is going to be a diverging lens. And take care that the other two are both the same type of lens. So it's going to be a diverging lens. Okay, then last up is our lasers and optical fibers. Now these lasers and optical fibers, the classic example that I think of is, well, either optical broadband. And please do say, if they ask you for an example of optical fibers, don't just say broadband, because most broadband is carried on copper cables. If you say optical broadband, then that would be fine, because that's what it is. So another example of uses of optical fibers is an endoscope. So an endoscope is it's like the kind of thing I brought into the lesson from Dr. Fairless that she used to look at bats in funny places, a long bendy set of cables that you can use to film round corners. Now, how this works is that the ray of light is totally internally reflected inside the glass fiber. Now, you might think that, well, if it's glass, surely the light is going to come out. But, oh, I can't write and talk at the same time. So totally, I'm just going to get rid of that. So totally internally reflected, otherwise known as TIR. So totally internally reflected. And we can see that each time it hits this side of the glass, it totally internally reflects, but not at all angles. If I shine the ray of light at too steep an angle, the ray of light will pass out of it. So if I shine my ray of light like so, it will change direction and it will hop and it will come out. So there is a special angle at which I can shine the light for it to stay totally internally reflected. And this special angle is shown over here on this diagram. So here we've got a light source, and this must be underwater. And there we've got our air above it, and we've got water below it. Okay, now as I increase this angle of incidence here, don't forget the angle of incidence is always between the normal and the ray. As I increase that angle of incidence, the light bends more. Well, if you look at this angle here, this here is the critical angle. This critical angle is the angle for this particular substance at which the light is totally internally reflected. Now at this angle, the ray of light actually just goes along the boundary. That's the minimum angle at which light needs to hit it to stay inside. Okay, and we say it stays inside, but it just goes along the boundary there. Okay, angles bigger than the critical angle, it's totally internally reflected. Now, because each material bends light by a slightly different amount, each material also has its own critical angle. So if we know the refractive index of a substance, we can work out the critical angle. Or if we know the critical angle, we can work out the refractive index. Okay, so examples, other things you need to know about this are, examples are an endoscope. Now for operations, you might also need to know that an endoscope might contain a torch to send light into the body, a camera or a fiber which carries the reflected light back to a camera device which is on the outside of the patient. You wouldn't normally shove a camera inside someone. But it might also contain some optical fibers which carry laser light, and the laser light can be used for minor operations. So you can snip bits of flesh off with an endoscope. So that will be your keyhole surgery, where you have a really small hole is made in you, and they can do all sorts of amazing operations on the inside of you. So if we now start to look at a couple of practice questions just before we sign off. Here we have figure 1 showing us a ray of light travelling through a semicircular glass block. Angle of incidence is labelled I. Here's the ray box. We're going from air into glass. Angle of incidence I equals the critical angle for the glass. Okay, complete figure 1 to show what happens to the ray of light at the glass to air boundary. Now, if I is at the critical angle, let's just go back and have another look at our diagram on the last page. At the critical angle, for this water is 48.8, the ray goes along the boundary. That's what happens at the critical angle. So we're going to do exactly the same thing. For our 1 mark there, we're just going to draw it along the boundary, which you probably have to use a ruler for, which I can't on my screen, so like so. Okay, and let's have a look at the next question. Okay, so this one, the critical angle for the glass is 41 degrees. Calculate the refractive index of the glass. Well, we're going to need to use that equation on the last slide. So n equals 1 divided by sine of the critical angle. So refractive index will be n equals 1 divided by the sine of 41, which equals, I'm going to do that one in my head, 1.5. Not really, I can't do sines in my head. Okay, equals 1.5. Okay, Now, ladies and gentlemen, that is the end of part 1, physics. Please feel free to watch this one again. Definitely over half term, before the exam, have a quick watch through it again, practice some of these questions, and we will build on this in class. Okay, ladies and gentlemen, thank you very much for your time, and I'm signing out. Thank you.